Okay, so today we are going to see some simulations of stochastic differential equations. Since here the students have various different background, so I would not assume any expertise in any particular coding language. So what we are going to do is that we would use just the spreadsheet, okay, which everybody knows to some extent, and just using the spreadsheet we would see that how to simulate a stochastic process from a stochastic differential equation. Okay, so when we want to do that, we first need to simulate a random variable, correct? Because stochastic differential equation involves a random variable, correct? So like Brownian motion. Okay, so we would see first how to simulate a Brownian motion. Before that, one must also see how to simulate a normal random variable, correct? Because Brownian motion has independent increments, and the increments are normal random variables. Okay, so we proceed in the following manner. We would first see that how to simulate a uniform random variable on interval 0 to 1. That is actually a default function given in almost every language. So spreadsheet also has one particular library function. But for generating a normal random variable, there is no particular library function, but using by composing two different library functions, we will be able to do that. And then from that, we would see how to simulate a Brownian motion, and then we would see that how to simulate a stochastic process from a given SD. Okay, so we start from here. So this is a new sheet where we would like to see that how to simulate. So let me write down: simulate a uniform random variable on closed 0 1. Okay, so here I call that x is equal to, so here I write down is equal to sign rand, and then write down this parenthesis, okay, and press enter. What we get a number between 0 and 1. So now if we press F9, that is a calculation key, then it would recalculate. However, for some technical reason, I would not press the F9 key. I'd rather use delete button. Okay, so I would place my selection to some blank cell and press delete button. So we are going to see different realization of the random variable. Okay, so all the time we are getting a number between 0 and 1, and these numbers are random sample from the population of which has distribution uniform on interval 0 1. Okay, so one can ask that, okay, how can I be sure that this is really coming from uniform distribution? I mean, that is also not difficult. One can actually have, instead of one particular cell, say 100 cells with the same random variable. So, and then one can plot histogram, okay, or say empirical CDF. Okay, so from that one can see that, okay, it is coming from that distribution. Okay, so we are going to do that later. For uniform we would not do that because it is coming from the library function. So we take it for granted that it is coming from uniform random distribution on interval 0 1. Okay, so now we take n is a normal random variable. Okay, so that we would like to generate. Okay, so what we do is that we take inverse of the CDF of normal random variable, okay, and that we compose with this uniform random number. So then the result what we are going to get would be a random variable, but that would have distribution, according to standard normal random variable. Okay, so let us see that. So here we see normal inverse. So normal inverse. So this is the inverse of CDF. Okay, here one should pick up this probability to be this. Okay, so inverse, and mean to be 0, and standard deviation, say 1, because standard normal we want, and then we close. So now here what we are getting here is a random number, not between 0 and 1, but so here this one is could be any real number, minus infinity plus infinity, and however it is coming from the population. This is a random sample from the population of normal distribution with mean 0 and variance 1. Okay, so let us see various different realizations. So far it is all positive, because the way we have defined, when capital X value, that means this second row, this thing is half or more than half, then this n is non-negative. Okay, however, if this is less than half, then you see that n is negative, and that is quite expected, because normal random variable is half of the time, with mean 0 is half of the time positive, half of the time negative. Okay, so we see that sometimes it is positive and sometimes negative. Okay, so now here this is the point when one can ask that, okay, is it really coming from normal random variable? Let us see the distribution. Okay, so for that what we do is that we would generate one array. Okay, array of this. Okay, so we start here. So is equal to normal inverse, and inside the probability I write down here directly rand. Okay, so this rand is the uniform distribution from 0 to 1, and then mean is 0 and variance is 1. Okay, so we are getting some number, and then I drag it for 100 such things. Okay, so I go to, so it is coming from 4 A103, and from here to here I select, and then I copy this formula down. Okay, so we have now 100 different realization of a normal random variable with mean 0 and variance 1. Okay, and now here we would like to see that what is this CDF. We can plot histogram or something, but here we plot. So here what we do, we take a rank of this thing. Okay, so this number, comma, then this whole list, whole array. Okay, so that is giving me the rank of this number. Okay, and then I would like to keep this array as it is, so we put dollar before the row name, so that if I drag the formula handle, the list selection does not change. Okay, so now we are done with the putting formula. Now we drag it. So this is the rank of these numbers. Now if we just plot, so here these numbers are between 1 to 100, because these are ranks, correct? These are ranks. But if I want to draw it versus so like 1 to 0 to 1, then you have to divide by 100. Okay, so let us do that. Equal to this, divide by 100, so that now it is ranked between 0 to 1, not between 1 to 100. Okay, so here we drag the formula down, so we got this thing. So now we just insert a scatter plot. Okay, so here this thing I don't need, so I just delete this thing. So this thing I need. So it is coming the reverse direction ranking. So so that it looks like CDF, I should put ranking from ascending order. Okay, so they need to look like proper CDF. So that we do here. Yes, now it looks like a proper CDF, correct? So see that it looks like a CDF, the cumulative distribution function of normal random variable, correct? So with mean 0 and variance 1, here I mean we did not have any realization beyond -3 and +3, and then here it looks like this. Okay, so this made us quite confident that what we have simulated is indeed normal CDF coming from normal random variable. Okay, so I delete this thing. Okay, so now if I want to simulate a Brownian motion, okay, using this random variable, what are you going to do? We have to add small normal random variables, okay, as increments, and then proceed. Okay, so that we do here. So here first we do the time axis. Say for example, this my column E is my time axis. So I write down time. Okay, so and then increment granularity you have to choose. So let us choose that say 0.1. Okay, so delta t is equal to say 0.1. Okay, so then time starts with say, so 0 is actually Brownian motion is 0, so we do not need to simulate anything. So time 0, and this is the Brownian motion. Okay, so now here the next time step would be first is 0, next time step is equal to the above one plus this delta, this thing. However, we don't want to move this because the delta t, this value should remain as it is as we move the formula handle. So here we would go to 100 steps. So we go at 103, and then we create the time axis. So time axis is done. Okay, so here last number should be like 10, correct? 9.9, huh? Last number is 9.9. So time axis is done. Now for Brownian motion, what we need to do is that we need to recall the definition of Brownian motion. There, if the increment size is delta, then the Brownian motion increment is normal random variable with mean 0 and variance delta. Okay, variance delta. So here the normal random variable what we have obtained here had variance 1. Okay, so if we multiply with the standard deviation with this, then we are going to get. Okay, so what is the standard deviation? Variance is delta, and the standard deviation is square root of the delta. Okay, so here delta is 0.1. Okay, so what I do is that is equal to, so Brownian motion is increment, right? So for earlier thing whatever I had plus. Okay, so now square root, so sqrt square root of this number if 2, okay, f2, okay, so square root closed multiplied with this normal random variable what we have done already in the A column. Okay, so that would give me the Brownian motion's value at time 0.1. Okay, good. Now what we are going to do, we are going to get the whole realization. So that I have selected F column 100 many, and then we press down. So what we have obtained is the simulation of Brownian motion here. Okay, but we would like to check that how does it look like. Okay, so we are going to do that. We are going to plot it. We are going to insert one scatter plot here. Okay, so that is giving me, a particular realization of Brownian motion. Okay, good. And if we recalculate, so we are going to get another sample of Brownian motion. So let us see. So I go to a blank cell and press delete. So that would request spreadsheet to recalculate the sheet. So we would get a fresh set of new random numbers would be generated, and then from that whole path would be generated. Okay, so we see that here we have 0. So at time 0 Brownian motion is 0, but then when we run several times, so here it is going negative. Okay, but sometimes it goes also positive. Okay, so like this goes positive. So this is actually not precisely a Brownian motion. This is more or less a random walk type of things. However, here this is an approximation Brownian motion. Okay, because here with this granularity of 0.1. Okay, so but if you want better accuracy, you should have much smaller granularity. Instead of 0.1, maybe 10 to the power minus 3 or something. However, I mean, so these are the way to simulate a Brownian motion. Okay, so now we go to the case when we have a stochastic differential equation. So in the last week's lecture, we have seen Brownian bridge, correct? So that satisfies a certain stochastic differential equation. Okay, and then we have also seen a particular realization of the solution of that SD. Okay, and Brownian bridge has a very nice path. Okay, that particular realization we have seen that it was going from 0 to 1. Okay, and then so we would like to see that code. Okay, how to do that. So I come to Brownian bridge, so this page. So here, just as before, what we have done, we have taken a time axis. So this column A is time axis. So here increment is dt. dt is equal to 0.01. Okay, so 0.01 increment. And here, so we have 0.01, 0.02, 0.03, etc. We have done it for 102. Correct, so that we get exactly 101 number of points. Okay, so that last number is 1. Okay, so we have partition of 0 to 1 with 101 number of points, or in other words 100 number of sub intervals. Okay, so here what we are simulating is the Brownian bridge from point 0 to point 1. So this is point 0, this is point 1. So see, 1 is here, 0 is here. So this is the time axis, horizontal axis is the time axis, and here vertical axis is the Brownian bridge value. So let me do this so that it looks better. Okay, looks good. Now we, before explaining the formula here, so let us see how realization changes if we ask the sheet to recalculate. So here it changes. So the bridge point 0 and 1 is pinned here. So sometimes Brownian bridge is also called pinned process, correct? So pinned here, and we see that for various different realization, we are seeing various different paths connecting 0 and 1. Okay, good. So this plot clearly shows that the code, whatever we have written, so that is doing what it's supposed to do. Okay, so let us see the code here. So this code is very simple. It's just a spreadsheet application. So now we recall the stochastic differential equation, that is dxt is equal to xt divided by 1 minus t dt plus dwt. Okay, so what we do is that here the increment is dxt. So we look at the increment. So whenever I write down increment, so this is like, every cell is increment plus the earlier time, so earlier value. So earlier value, first value is 0, so 0 plus, so b2 is 0, correct, b2 is 0. So it depends on many things. It depends on b2, so it's 0, and also it depends on the b value and a value. So b value is here 1, okay, so b is equal to 1 and a is 0, okay. So but a actually, a does not appear in the SD, a appears in the initial condition, okay. So here f1 is basically b value minus b2. b2 is this earlier state, okay. So this is 1 minus x, okay. So 1 minus x divided by 1 minus a2. A column is time column, so it is 1 minus t, okay. So numerator you have 1 minus xt, and the denominator you have 1 minus t, and then h1 is the dt term, 0.01 dt term, this is green color, and then you have Brownian motion, okay, increment. Okay, so as we have seen earlier in the earlier sheet, the normal random variable inverse CDF of the inverse of that, okay, and then this rand, so that is going to give me the probability of that, and then with mean 0 and variance square root of this dt, okay. So that is Brownian increment. So this whole quantity is the dbt. It stands for dbt, okay. Okay, so that is the formula here, and then as we go down we see that just so started for b2, the b2 becomes b3, okay, and a2 becomes a3, and all other things are as it is, huh? So that with respect to time, 1 minus xt divided by 1 minus t, that only changes with time t, and dbt is the same increment, however independent realization. So all the time a different cell calls for the same library function rand, one gets independent realization of that uniform random variable on 0 1. Okay, so that is the way it is done here. Okay, I think I have pretty much explained how to simulate a Brownian bridge from the stochastic differential equation. Okay, next we would see simulation of another stochastic differential equation, okay. So let us simulate geometric Brownian motion, okay. So that we can do actually on this sheet itself, but okay, let us go to the earlier sheet 4 where we have simulated the Brownian motion. Okay, so the geometric Brownian motion, already we know the definition, so let us recall. So geometric Brownian motion that satisfies the following stochastic differential equation, that is dxt is equal to particular value, say a times xt dt plus say b times xt dwt. Correct. So that is the equation, stochastic differential equation for geometric Brownian motion. So as before, we have to specify what value of a and b we are going to select here. So let us write down those. Okay, so say a is equal to say we take say 1, just 1, okay, and b is equal to, we also take this say 1, okay. So a is equal to 1, b is equal to 1, and then dt we also need to specify, say we select the same dt as 0.1, okay. So same dt we take, and then here we would like to write down this xt, that is geometric Brownian motion, okay, xt. So I write down gbm here, gbm. Okay, so now GBM has actually, this SD has a strong solution, and the strong solution has also a closed form. Okay, we know that we can actually simulate from the closed form solution itself. However, for many SD, one does not have closed form solution. So we were actually trying to learn how to simulate from the SD itself. So here we would simulate from this SD. So this is a starting point. I should mention what should be this. So starting point, say x0 is equal to, say, can I put 0? No, I cannot put 0, because if it starts from 0, right hand side becomes 0, because a times 0 dt plus b times 0 dwt. So dxt would be 0. So increment would be 0 throughout the time horizon. So the whole process will be just trivial 0 process. Okay, so that is the reason that we would not put 0 but some x. Okay, so a is equal to, say, 1, b is equal to 1, small x is equal to, say, also that we put at 1. Okay, so now we have fixed all the parameters what we need. Now we can, placing all the variable values or all the parameter values, now we would be able to simulate the geometric Brownian motion process by by discretizing the stochastic differential equation, which is written here. It is dxt is equal to a times xt dt plus b times xt dwt, starting with x0 is equal to small x. Here we have also fixed the values of a, b, and initial point x, that is 1, all are 1 here. Okay. Now when we try to simulate, we would first need to find out x at the dt time, that is 0.1 for our case, and then when we compute that, based on that we find out x at 2 times dt, then based on that we need to find out x at 3 times dt, etc. So now here for every time x of that dt time is earlier x0 plus the increment. The increment is discretization of this equation on the right hand side. So here, therefore, the formula is that this is equal to the earlier geometric Brownian motion value, this is the initial this thing, plus then the increment. The increment part is a times, and then xt is again the initial is this thing, times then dt is 0.1. okay, now plus now the parameter is b, so b times we multiply xt, that is here, and then we need to multiply now increment of Brownian motion. So that is Brownian motion is on the f column, so here it is this difference of this number minus this number. Okay, fine. Okay, so this is going to give me the Brownian motion value at the dt time. Okay, so now we need to do it for all of the time. So for that we are going to replicate this formula in other cells. Before that we fix these parameter things so that they do not change the position. So we put this dollar here. This is for dt, and this is for b, and here this is all fine. Okay, so it should work. Okay, so now we go to the end. Okay, and go to the top. Okay, and drag this formula till the end. Okay, now this is geometric Brownian motion simulation. You see that for Brownian motion, which comes under f column, may often become positive or negative, but this geometric Brownian motion is always positive. It's never negative. Okay, so now what we do is that we plot. Okay, we plot this time, I mean Brownian motion and geometric Brownian motion in the same frame against time, so that we can compare between the Brownian motion and geometric Brownian motion's dynamics. We can also try to see that how Brownian motion influencing the dynamics of geometric Brownian motion. Okay, so here we insert a plot. Yes, so insert a plot here. Okay, so we place the plot to my right. Okay, so here we can see that this green line is representing the path of geometric Brownian motion, and blue line is representing the path of Brownian motion. If I recalculate this by pressing F9, so we obtain another dynamics, another realization, okay, of the same dynamics. Okay, so we see that here Brownian motion is the blue line, and geometric Brownian motion is the green line. So this blue line now suddenly appears very straightforward. It looks like it has less fluctuation, but that is not the case. It is just because of the scaling, because this geometric Brownian motion goes went so high here, so that's why it is not appearing as large. But here this is the plot for corresponding Brownian motion. Okay, so here we put both the things. So this is the actual dynamics of Brownian motion there, which is now appearing this thing because the corresponding GBM is having high magnitude. Okay, so maybe few more running. So when Brownian motion is becoming positive here, so then GBM becoming too large, like 600 etc. So then that's why compared to that, this lines looks like pretty straight, horizontal. Okay, so okay, I think we have a pretty good idea now about simulation of geometric Brownian motion using spreadsheet, Excel spreadsheet. Okay, fine. Okay, thank you very much.